Section 1.3, Trig Functions. The intent of this section is to remind you of some of the more important, from a calculus standpoint, topics from a trig class. One of the most important, but not the first of these topics, will be how to use the unit circle. We will leave the most important topic to the next section. First, let's start with the 6 trig functions and how they relate to each other. We have the cosine of x, the sine of x. The tangent of x is equal to the sine of x over the cosine of x. Cotangent of x is equal to the cosine of x over the sine of x, which is equal to 1 over the tangent of x. Secant of x is equal to 1 over the cosine of x. Cosecant of x is equal to 1 over the sine of x. Now recall as well that all the trig functions can be defined in terms of a right triangle. Here's your right angle, there's your theta. This is the adjacent angle, this is the opposite angle, and then this is the hypotenuse. Now from this right triangle, we get the following definitions of the 6 trig functions. The cosine of theta is equal to the adjacent divided by the hypotenuse. The sine of theta is equal to the opposite over the hypotenuse. The tangent of theta is the opposite over the adjacent, whereas the cotangent of theta is adjacent over the opposite. The secant of theta is the hypotenuse over the adjacent, and the cosecant of theta is the hypotenuse over the opposite. Remembering both the relationships between all 6 of the trig functions and the right triangle definitions will be useful in this course on occasion. Next, we need to touch on radians. In most trig classes, instructors tend to concentrate on doing everything in terms of degrees, probably because it's easier to visualize degrees, and the same is true in many science classes. However, in a calculus course, almost everything is done in radians. The following table gives some of the basic angles in both degrees and radians. The degree, we have 0, 30, 45, 60, 90, 180, 270, 360. How are they written in radians? 0 is 0, 30 is pi over 6, 45 is pi over 4, 60 is pi over 3, 90 is pi over 2, 180 is pi, 270 is 3 pi over 2, 360 is 2 pi. Now, know this table. We may not see these specific angles all that much when we get into the calculus portion of these notes, but knowing these can help us to visualize each angle. Now, one more time, just make sure this is clear. Be forewarned, everything in most calculus classes will be done in radians. Let's next take a look at one of the most overlooked ideas from a trig class. The unit circle is one of the more useful tools to come out of a trig class. Unfortunately, most people don't learn it as well as they should in their trig class. Below is a unit circle with just the first quadrant filled in with the standard angles. The way the unit circle works is to draw a line from the center of the circle outwards, corresponding to a given angle. Then look at the coordinates of the point where the line and the circle intersect. The first coordinate, i.e. the x-coordinate, is the cosine of that angle, and the second coordinate, i.e. the y-coordinate, is the sine of that angle. We've put some of the basic angles along with the coordinates of the intersections on the circle. So again, the cosine of the angle is the x-coordinate, and the sine is the y-coordinate. So here you have 0, and then it goes to pi over 2, and then it goes to pi, and then it goes to 3 pi over 2, and then a 2 pi. Now, this also represents 1, 0. This represents 0, 1, negative 1, 0, and then 0, negative 1. Here's our angle pi over 6. Here's our angle pi over 4, and then pi over 3. Now, so from the unit circle, we can see that the cosine of pi over 6 is equal to the square root of 3 over 2, and the sine of pi over 6 is equal to 1/2. So let's go back and verify that. So the cosine of pi over 6 is the square root of 3 over 2, and the sine of pi over 6 is equal to 1 over 2. Also remember how the sines of angles work. If you rotate in a counterclockwise direction, the angle is positive, and if you rotate in a clockwise direction, the angle is negative. Recall as well that one complete revolution is 2 pi. So the positive x-axis can correspond to either an angle of 0 or 2 pi, or 4 pi, or 6 pi, or negative 2 pi, or negative 4 pi, etc., depending on the direction of the rotation. Likewise, the angle pi over 6, to pick an angle completely at random, can also be any of the following angles. Pi over 6 plus 2 pi is equal to 13 pi over 6, which means you start at pi over 6 and then rotate once around counterclockwise. Pi over 6 plus 4 pi is equal to 25 pi over 6, which means you start at pi over 6 and then rotate around twice counterclockwise. And then pi over 6 minus 2 pi, which is equal to negative 11 pi over 6, which means you start at pi over 6 and then rotate around clockwise. And then pi over 6 minus 4 pi, which is equal to negative 23 pi over 6, means you start at pi over 6 and then rotate around twice clockwise. Now, in fact, pi over 6 can be any of the following angles. Pi over 6 plus 2 pi n, where n can be equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. In this case, n is the number of complete revolutions you make around the unit circle, starting at pi over 6. Positive values of n correspond to counterclockwise rotations, and negative values of n correspond to clockwise rotations. So why did we only put it in the first quadrant? Well, the answer is simple. If you know the first quadrant, then you can get all of the other quadrants from the first with a small application of geometry. And you'll see how this is done in the following set of examples. So we're going to evaluate each of the following. So the first one we want to first find is the sine of 2 pi over 3 and the sine of negative 2 pi over 3. So the first evaluation in this part uses the angle 2 pi over 3. That's not our unit circle. However, notice that 2 pi over 3 is equal to pi minus pi over 3. So that means 2 pi over 3 is found by rotating up pi over 3 from the negative x-axis. This means that the line for 2 pi over 3 will be a mirror image of the line for pi over 3, only in the second quadrant. The coordinates for 2 pi over 3 will be the coordinates for pi over 3, except the x-coordinate will be negative, since it's in quadrant 2. And likewise, for negative 2 pi over 3, we can rotate that negative 2 pi over 3, which is equal to negative pi plus pi over 3. So this angle can be found by rotating down pi over 3 from the negative x-axis. This means the line for negative 2 pi over 3 will be a mirror image of the line for pi over 3, only in the third quadrant, and the coordinates will be the same as the coordinates for pi over 3, except both will be negative. Now, both of these angles, along with the coordinates of the intersection points, are shown on the unit circle. So here, again, we have pi over 3, we have 2 pi over 3, and we have negative 2 pi over 3. And so, from this unit circle, we can see that the sine of 2 pi over 3 is the y-coordinate, which is the square root of 3 over 2. And then we can see that the sine of negative 2 pi over 3 is the y-coordinate, which is negative square root of 3 over 2. And remember that in the first quadrant, both x and y are positive. In the second quadrant, x is negative, y is positive. In the third quadrant, they're both negative. In the fourth quadrant, y is negative and x is positive. This leads to a nice fact about the sine function. The sine function is called an odd function, and so for any angle we have, the sine of negative theta is equal to negative sine of theta. Now for the next example, we notice that 7 pi over 6 is equal to pi plus pi over 6. So this means we would rotate down pi over 6 from the negative x-axis to get to this angle. So let's take a look at pi over 6. And so we're going to rotate here to get negative 7 pi over 6. So, as with the last part, both of these angles will mirror the images of pi over 6. so in the third and the second quadrants, respectively, and we can use this to determine the coordinates for both of these new angles. Both of these angles are shown in the following unit circle, along with the coordinates for the intersection points. So from this unit circle, we can see that the cosine of 7 pi over 6 here, which is the x-coordinate, is negative square root of 3 over 2. And the cosine of negative 7 pi over 6 is the x-coordinate, which is negative square root of 3 over 2. In this case, the cosine function is called an even function, and so for any angle we have, cosine of negative theta is equal to the cosine of theta. Now for part C, here we should note that 7 pi over 4 is equal to 2 pi minus pi over 4. So 7 pi over 4 and negative pi over 4 are in fact the same angle. Also note that this angle will be the mirror image of pi over 4 in the fourth quadrant. The unit circle for this angle is the following. So here is negative pi over 4, here is 7 pi over 4. And again, that is a mirror image of, we have our pi over 4. So that means that the x-coordinate is positive and the y-coordinate is negative. Now, if we remember that the tangent of x is equal to the sine of x over the cosine of x, we can use the unit circle to find the values of the tangent. So the tangent of 7 pi over 4 is equal to the tangent of negative pi over 4, which is the sine of negative pi over 4, which is the y-coordinate, negative square root of 2 over 2. And the cosine of negative pi over 4 is the x-coordinate, which is positive square root of 2 over 2. So dividing it both by itself with a negative becomes negative 1. And then also on a side note, notice that tangent of pi over 4 is equal to positive 1. And we can see that the tangent function is also called an odd function. And so for any angle, we will have tangent of negative theta is equal to the negative times the tangent of theta. Now for part D, here we need to notice that 25 pi over 6 is equal to 4 pi plus pi over 6. In other words, we've started at pi over 6 and then rotated twice because of the 4 pi to end back up at the same point on the unit circle. This means that the secant of 25 pi over 6 is equal to the secant of 4 pi plus pi over 6, which is equal to the secant of pi over 6. Now, let's also not get excited about the secant here. Just recall that the secant of x, which is equal to 1 over the cosine of x, and so all we need to do here is to evaluate a cosine. So therefore, the secant of 25 pi over 6 is the same thing as secant of pi over 6, which is equal to 1 over the cosine of pi over 6. We know that the cosine of pi over 6 is the square root of 3 over 2. And then therefore this is equal to 2 over the square root of 3. Now again, we may need to rationalize the denominator here to simplify this a little further. So if we did, we'd have to multiply both the numerator and denominator by the square root of 3 to get 2 times the square root of 3 over 3. So in the last example, we saw how the unit circle can be used to determine the value of the trig functions at any of the common angles. It's important to notice that all these examples use the fact that if you know the first quadrant of the unit circle and can relate all the other angles to mirror images of one of the first quadrant angles, you don't really need to know the whole unit circle. If you'd like to see the complete unit circle, I've got one on my Trig cheat sheet that is available on Canvas. Another important idea from the last example is that when it comes to evaluating trig functions, all that you really need to know is how to evaluate the sine and cosine. The other 4 trig functions are defined in terms of those 2, so if you know how to evaluate sine and cosine, you can also evaluate the remaining 4 trig functions. We've not covered many of the topics from a trig class in this section, but we did cover some of the more important ones from the calculus standpoint. There are many important trig formulas that you will use occasionally in a calculus class. Most notably are the half angle and double angle formulas. If you need reminded of what these are, you might want to download the Trig Sheet, the Trig cheat sheet, as most of the important facts and formulas are from a trig class are listed there.